Good morning, student. Welcome back to the fifth session of statistical thermodynamics. And again, I am using the university facilities of lecture capturing theatre. Today, I will discuss one of the important aspects of partition function, that is vibrational partition function. In my previous lectures, I have already derived translational partition function as well as the rotational partition function. And you will have a clear-cut idea about the translational motion as well as the rotational motion of diatomic molecules or even polyatomic molecules. And with the help of translational energy and rotational energy, we do derive the translational partition function as well as the rotational partition function. Similarly, now I am considering the vibrational partition function. And you all are aware of molecular spectroscopy, and you know the importance of this vibrational partition function. Most of the important thermodynamic parameters like entropy, enthalpy, free energy, heat capacity, as well as equilibrium constant can also be determined with the help of this vibrational partition function. And here you know that because we are concerned about the vibrational partition function, so we must know about the vibrational motion of diatomic molecules or polyatomic molecules. Now, here I would like to show you, before going into details derivation of vibrational partition function, we must know what is actually molecular motion and vibrational modes. Now, suppose I am talking about a molecule and it has 3 atoms. So, total number of atoms is 3. Now, you know that there is a term that is called the degrees of freedom. How many independent ways those atoms can move. And I am talking about a 3 dimension, x, y and z. And we have n atoms, so there are 3 degrees of freedom. So, I have written here 3n. Now, if you know the translational motion, so there is no problem whether it is a monoatomic or diatomic or polyatomic. So, in normal cases, there are 3 translational motion, of course in x direction and y direction and z direction. But if we are talking about the rotational motion, you know that if I am taking a diatomic molecules or if I take a polyatomic molecules, water, so it depends. If it is a polar molecule, linear molecules, so there are 2 rotational degrees of freedom, x-axis and y-axis, like that. If I am taking the non-linear molecules, so there are 3 rotational degrees of freedom. So, total 3 translational and 2 rotational. So, total number is 5. So, remaining is vibrational motion. So, I can write like that. I am giving one example, so you can understand these things. That is, for vibrational modes, if the molecule is linear, so it is 3n minus 5. And if it is a non-linear molecule, so it is 3n minus 6. Now, what about the vibrational motion? Suppose I am taking water, H2O. There are 3 atoms. So 3 into n is equal to 3 is equal to 9. 9 minus 6, 3 translational, 2 rotational. So remaining 3 is the vibrational motion. And that vibrational motion do affect the thermodynamic parameters. And of course, the partition function and other things, distribution of molecules. So I am giving why it is 3. Now it is possible in vibrational motion. One is symmetric stretching, another is the asymmetric stretching, another is the bending. I am just giving one simple example of what you know the Hooke's law and other things. If I take 2 ball and there is a spring, so there is a compression as well as the expansion. So you know all these things. I am not going into details about the Hooke's law and other things, but I am giving the types of the vibrations. Why these vibrations, mode of vibration is important? Because when I will derive the vibrational partition function, there will be different forms. For diatomic molecules, the formula will be different. For polyatomic molecules, the formula will be different. And of course, I will explain all these things. So you see, I am taking the water, it is a symmetric stretching. So you know this direction and this direction, so there is a symmetry. But if it is a asymmetric stretching, you see this type, this is also going, this is also. And third is the bending structure, 1, 3 directions. So that if you refer many books, so you can see the others example. For simplicity and for clarity and novelty, I am using this thing. So it is a fundamental aspects of the vibrational motion. Now I will come to that, what is actually vibrational partition function. Now as this is my style, whenever I start the things, I first give the final formula of the vibrational partition function. So here in the blackboard you can see 3 structure. First is the Q vibration, that is vibrational partition function, 1 over 1 minus exponential h nu kb and t. Here this nu is the vibrational frequency and kb as usual Boltzmann constant is the Planck constant. Now again if you see the red color or this diagram, this formula, where there is a slight difference in numerator and denominators. Here you have seen the formula is slightly different. Why I am giving these 2 formula? Because this first formula, which is available most of the common books, that is when we consider will not without 0 point energy. I will explain all these things. And the second formula, when we consider the 0 point energy, although because if you see the rotational partition function and the rotational energy and translational energy, where in quantum mechanics there is a 0 point energy and E 0, there is certain values here. I will explain these things. So one is, again I am just repeating first formula, which is very common, which is without 0 point energy for diatomic molecules. And second, with 0 point energy, it is slightly different, this thing. And I am also mentioning 2 books, because if you refer the books of thermodynamics for chemists by the Glaston, very old book, in that book the simple formula is given. And if you see the Macquarie and others book is also Levine and Atkins and other things, so you will get this. So what I think that I will derive both the things as well as the considering without 0 point energy and with 0 point. And there is a third formula we have also seen, where I am taking a product of, if I take the polyatomic molecules, suppose water molecules, and there are 3 vibrational frequencies, then of course the formula will be different. So overall there are 3 formulas, and if you want to learn details things, I have also taken some derivation from Inflibnet E Pathshala. by Professor A.K. Bakshi. He has very nicely explained in E-Pathshala the partition function, vibrational partition function without 0-point energy and with 0-point energy. And for the last formula, if I consider the polyatomic molecules, so here you see that S, if I write, so that actually you see that there is a summation product of all the things, and here I am taking the S, and this S, if it is a linear polyatomic molecule, the S may be 3n minus 5, and if it is a non-linear molecule, so S may be 3n minus 6, because the vibrational degrees of freedom are separable. So therefore, total vibrational partition function is the product of the vibrational partition function of each degrees of freedom. So that is the things, I think. Yes. Okay. Now I am starting the derivation, and as usual, and because this is the third series of lecture related to the partition function, you know the general formula of partition function, which is very simple, summation of course here, because we are talking about the vibrational partition function, so I have taken the vibrational quantum number, that may be 0, so that may be 0, 1, 2, 3, right up to, it will go up to infinite. So, but one point is important here. In rotational partition function, you have seen when I have taken the rotational partition function, that is depends upon the degree of degeneration, 2j plus 1. But here, please bear in mind that when you derive the vibrational partition function, and that lines are not closely spaced, and the degree of degeneracy is not there. So it is a non-degenerate, each normal mode of vibration behaves like a one-dimensional quantum harmonic oscillator. And so there is only one possible wave function for each vibrational quantum number. And of course, there is no internal symmetry in a single one-dimensional partition function. I will come to that point. So therefore, don't consider here it is a non-degenerate system. So don't give any values of the G. Now, second is the question of E vibration. Like the rotational partition function, we do use rigid rotator for the diatomic molecules. Here, in order to get the values of vibrational energy, I have to take the simple harmonic motion, simple harmonic oscillator, because we consider that most of the oscillations are harmonic, but of course there is an approximation. So therefore, sometimes we call that is a simple harmonic oscillators approximations, because we have to consider the anharmonicity also. But of course, anharmonicity correction must be made, but that anharmonicity does not affect. So therefore, you should not worry about the anharmonic oscillations and other things. So our part is now, we have to substitute the value of this vibrational energy, and this is just like Boltzmann constant and temperature, so there is no problem. Now see it is very carefully. Now I have to derive the equation. I know G, it is non-degenerate, so there is no problem of the G, degree of degeneration. Now the second problem is the question of how do I calculate the vibrational energy, of course with the help of harmonic oscillator approximation. Now you can ask me, sir, why you are talking about the approximations? And you know that the vibrational energy level are not closely spaced, but when we increase the vibrational quantum number, you see that there is a change in spacing. But basically we will consider this V0 nu 0 to like that. So that is important. So directly you can write that the vibrational energy which can be derived from harmonic oscillator approximation, that is E vibrational is equal to V small v. It is the vibrational quantum number. Don't get confused with that. It is nu. Nu is the vibrational frequency. I'll also explain. So this is, so first part is over. We know the G, it is non-degenerate. Second part is that we know the E vibrational. So I have to apply the E vibrations in our main formula and we'll get the result. Now one thing is important here, that whenever we derive the vibrational energy, which is like that, I have already given this formula. But another thing is important. If you, I am not going to discuss about the Hooke's law and that pendulum structure and this spring model, how to calculate the force constant and the displacement. But you should have a simple elementary knowledge about these things. We have to use only this formula is enough for derivation of the vibrational partition function. This formula is enough. But what I do, that these vibrational, because in sometimes there may be a possibility of simple numerical problems related to the calculation of the force constant, So if you want to calculate the force constant, so then we can write the vibrational frequency is equal to 1 by 2 pi Ki mu, and that Ki is the force constant and mu, you know that, is the reduced mass. And during the derivation of rotational partition function, I have already told you, if it is Ma plus Mb or whatever you write. So you can write like that, Ma Mb, Ma plus Mb, or mu is equal to, you can write that, Ma Mb divided by Ma plus Mb. So I am not going into details of these things. So this is actually Hooke's law, calculation of the vibrational frequency. So now I will derive these things. I have to substitute the value of E vibrational, G, no problem, G it is non-degenerate, and just we will get the final equation. First I will consider without the 0 point energy, and second we will consider the with 0 point energy. Yes. Now one thing is important, because you know that whenever we write the formula, you know that I have written here 1 final formula 1 minus exponential minus h nu Boltzmann constant and T. These are final formulas. So far I have not derived, but before derivation I would like to explain all the elementary things. So you know that in rotational partition function there is a very important parameters that is called the characteristic rotational temperature. Similarly, here is also one important parameters that is called the characteristic vibrational temperature, and that is actually what I can write like that H Planck constant vibrational divided by Boltzmann constant, and that is denoted as theta vibrational. And if you ask me, sir, what is that? And each of the molecules, if you see here, if I am taking about the hydrogen, if I am talking about the HCl, if I am talking about the oxygen, nitrogen, so there is a, and partition function is a dimensionless quantity, but here the temperature is Kelvin. You see these are the value, and this indicates the temperature at which the energy of vibration is equal to kT. That means if I plot, see the, suppose this is vibrational level, this is different vibrational energy level, and in that case generally kT is maybe approximately maybe, so that vibration that is called the characteristic vibrational temperatures. And at the end of the lecture I will show you what is the importance of this thing, because sometimes in any objective type question or multiple choice question the examiner may ask that with the help of characteristic vibrational temperature how one can calculate the vibrational partition functions, and there is some condition that if characteristic vibrational partition function is greater than T and the T is normal, suppose 298 or 300 or 400, so Q vibrational value is around 1, which means that only the ground vibrational state is populated. On contrary, if the Q vibrational is less than T, many vibrational states are populated. So I'll explain these things, how do you calculate these things if the temperature is very high. And I have taken the values of this characteristic rotational temperature from the books of physical chemistry by Levine. So it is available. Now let me summarize that today. Now I am going to derive the vibrational partition function. Before I go for derivation, I explain to you what is degree of degeneracy in that case. Again and again I am saying that it is a non-degenerate level because we are considering one dimensional harmonic oscillator. You have seen the photographs. So G. Second, I discuss about the E vibration that we will derive from the simple harmonic oscillator approximation. Third, I discuss about the characteristic vibrational temperature. Now I will derive. The derivation is very simple. So I have to take the board. Yes. Eraser. Okay. So derivation. Please bear in mind, I am using without 0 point energy. If I use that black color or this color. So, our formula is that Q vibrational is equal to summation V is equal to 0, V is equal to infinite, no question of G, exponential minus E vibrational divided by Kb Boltzmann constant and T. Is it clear? Now the value of E vibration as per the simple harmonic oscillator, V plus half H nu. V is the vibrational quantum number and this is vibrational frequency in terms of hertz. In some books, what happened, if you see the Glaston, old Glaston, and the vibrational frequency is given in terms of centimeter inverse 1. Then of course, you know that C by lambda, and it is C, in some books it is omega, or some it is a nu R is also. Vibrational in terms of wave number. So in somewhere, sometimes it is given that like H C nu bar, like that. So don't get confused. Both are correct. One is in terms of hertz, another is in terms of centimeter inversion. You should be very careful while solving the numerical problem. Otherwise, there is no problem about these things. Now, what I am doing, that if you know that, so this like that. So V is equal to 0, V is equal to 1, V is equal to 2, V is equal to 3, like that. So it is 0 point energy. So if this V is equal to 0, so what I will do, that at 0 point energy, that means E0, because we are not considering here. So that is because this is equal to 0, so we will get the half H nu. This is the value of vibrational energy or 0 point energy. It is 0 point energy. 0. So net vibrational energy, it must be, again I am using this formula, that V plus half H nu minus half H nu. So you know that this half H nu, half H nu. So what I am getting, again I red color, I can use these things. So actual vibrational is equal to V H nu. So it is E vibration. So I have to substitute the values of this. Don't get confused. This is vibrational quantum number and this is vibrational frequency. Or in some books it is written in place of V, you can write small n also. But here I am just using, this is different. It is vibrational frequency. Again and again I am saying same thing. Now, just a minute. Yes, that's good. So, summation, yes. So, summation write exponential minus V H nu divided by KB T. Now simple. Now one thing is, please remember that because you have already studied the translational, you have already studied the vibrational, rotational, everywhere that summation is replaced by the integration. But here you need not to be worried about the integration because that lines are not closely spaced, so integration is not required. So simply we do the summation, and you know that this is a very simple formula. That means it's a geometric series like that. That means if I write that E nx summation 0 infinity, you know that is very simple. 1 plus exponential minus x, exponential minus 2x, exponential minus 3x, like that, dot, 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 dot. Similarly, it's a geometric series. If I use that x, if I write x is equal to h nu divided by kbt, what I can write? Again, I can write in the red color. So 1 plus minus h nu divided by kbt, very simple, plus h nu 2h nu kbt, so on. That means dot 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 like that, n h nu 3h nu kbt. Or what I can write like that, I can write like that, 1 plus ex 1 plus, you see, exponential minus x 2 exponential minus x 3, like that. Listen. So it is a geometric mean, and finally I can get, I can write in YOLO that, or even in blue color, it is like that, 1 minus e minus x minus 1, that will get this final example like that. So it can be recognized as binomial expansion of these things. So if you don't understand the mathematics, because some biology students are also here, so I'll explain the things. So when I substitute the value of this, so I will get 1 final equation divided by 1 minus exponential minus h nu kbt. So in a red color, what is my final value of vibrational partition function for diatomic molecules without considering the 0-point energy. So that is 1 divided by 1 over 1 minus exponential h nu. And as we know that h nu divided by kb is equal to theta vib. So I can write like that, 1 divided by 1 minus theta vibration divided by k. Also, this is also one form. Now, see here what I am doing. I am using what I am using the no 0-point energy. no 0 point energy. And my final equation is, again I am writing same thing, Q vibrational one divided by 1 H nu divided by kBT. Now, and using that simple formula, summation of 0 to V0 xn, like that is a very simple formula, we can calculate this. But suppose now I will consider the same 0 point energy. So, and that formula is, if I write YOLO here, I will explain, but here I can use that E is equal to V plus half H omega. So, I have to consider everything. That means, if I divided by KT. So, what is slightly different here, generally we use only one thing, but here I have to calculate the V plus half H nu divided by kBT. So, for biology student, because it is a very simple geometric means, and we calculate these things. But for geometry, for biology student, I am just showing you one of the simple formula. By that one can derive all these things. I will explain again, just a minute. And this, yes. So, it is again, it is not for mathematics students, it is for the biology students. How I solve these things, you know, that in our first case, we have used this formula. And V H nu KT. K is the Boltzmann constant, it's Boltzmann constant. I have already solved, I just not repeat these things. So, I am using this 1 plus E, and of course, this value of x is less than 1, and we will get this final formula. And this formula can be treated as a binomial expansion of this thing. So, I am getting this formula. But now, for when I consider the 0 point energy, so I have to slightly modify that equation. That means, yes, you see here. Why this formula is different? Because here I am taking E vibrational equal to plus half okay. So, what I will do in summation 0 infinite exponential minus V plus half H nu divided by kBT. And if I just solve it, I will get two things. I can write first, this is, I can write exponential minus H nu divided by 2 kT, because if I solve it, this, and second I will get normal V H nu divided by kBT. So, if I just take it out from outside, that means I can write like that, exponential minus h nu 2 kBt, then summation exponential minus just normal, just like h nu divided by kt, which is similar to our previous session, but only one additional thing is there. So mathematically, just you see this thing. Same thing I have written. Suppose x is this, and in place of v I have written n. X means x is just like h nu divided by kBt. So this formula is exactly same what I have written here. X divided this thing, and then if we solve it, but always remember that this is actually for x is always less than 0. So I will get the same formula like that. So now I am coming to again derivation part. Last, already. No. Okay, now I will solve this. With with 0 point energy. Same thing I have already written here, 0 to infinite exponential minus v plus half h nu divided by kBt. So again I change the normal color, just 2 minutes. So if I write exponential minus h nu 2 kBt or kt like that, summation. Okay. So exponential minus v, just like your old system, h nu divided by kBt. So if I expand the same, like same, if I expand, same thing. So exponential minus h nu 2 kBt bracket 1 plus exponential minus h nu kBt plus exponential minus 2 h nu kBt plus dot 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 like that, exponential minus 3 h nu. Same expression, one additional thing is there. And so that is exponential minus h nu 2 kBt 1 divided by 1 minus h nu kBt or like that. So finally with 0 point energy I am getting exponential minus h nu divided by 2 kBt divided by 1 minus exponential h nu. क्लास ले रहे हैं, बोलिए? हैं लेक्चर है, 5 मिनट 10 मिनट में हो जाएगा. So you see the final equation. This is with 0 point energy. Now, if I compare with that without 0 point energy, color will be different, so that you can get information. 1 minus exponential h nu divided by kBT. So, what is the difference between the with 0 point? Only one additional formula is there, and here is addition. So, and this, as I already told you, that this h nu divided by 2 kT is equal to characteristic rotational temperature. So, what Q of vibrational equal to what we can write exponential minus theta vibrational divided by 2T, okay, divided by 1 minus exponential minus theta vibrational divided by T. So, this is our first formula, and here same thing if I can write 1 minus theta vibrational divided by T. So, dear student, don't get confused, because there are two forms, but the mathematical solution is exactly same. We use the geometric mean and binomial expansion. Only difference is that if we consider the 0 point energy, I have to use this big formula, and if it is a without 0 point energy, most of the conventional books you will have this formula. This is now the last part is the 1 or 2 application. I think I do make my point clear. So, yes. So, now you just compare my first figure. Now, the last point is that the application, whenever I teach any subject, I must tell the students what are the importance of that vibrational partition function. As usual, that in translational partition function and rotational partition function, one of the most important applications is many thermodynamic parameters, entropy, enthalpy, internal energy, heat capacity can also be determined. And that is another big chapter, the application of partition function for the determination of equilibrium constant. But one point I must emphasize here, that you have already studied the transition state theory in M.Sc first semester, and when I do teach the the transition state theory or absolute reaction, I use the derivation of Wien-Jones and Eyring equation, and you remember that the role of partition function there. There are two partition functions, one is translational, another is the vibrational partition function, in order to understand the transition state, because that at transition state particular molecules experience acute vibrations. So, therefore, we will use the vibrational partition function. So, I have written that the vibrational partition function is very useful in the transition state theory. And when I have gone through the literature, I am very happy to inform you that, of course, in spectroscopy also, vibrational partition function is paramount importance in various role in infrared spectroscopy, molecular structure. But I have also seen in the literature that the scientists who are working on the astrophysicist or astrochemistry, astrophysical chemistry, the role of the energy distribution among the different molecules in various stellar environments. Of course, it is not related to the M.Sc students, but just for general knowledge, I would like to share this information that these vibrational partition function is of course useful for the studies of various stellar environment where different types of molecules are there. So, how that distribution of molecules among their vibrational level. Now, the last part is always I give some numerical problems because if you understand the formula, and the formula I have already derived, Q of vibrational, it's very simple, 1 minus exponential minus h nu divided by kBt, without considering the that 0 point energy. So for the biology students or other things, most of the university question paper or NET CSIR question paper, you will see that they ask the calculation of vibrational partition function. So very simple, that means if you know the values of, it is a standard Planck constant, then Boltzmann constant, then temperature and vibrational frequency, you can, whatever the value of exponential, suppose it is 12.25. So exponential minus 12.25, it will get the values of things. So I am giving, it is a homework that I am giving some example, that suppose you have to calculate the vibrational partition function of nitrogen, vibrational partition function of hydrogen, and vibrational partition function of iodine molecules. And I am giving the vibrational frequencies 2360 centimeter inverse 1, 439. It is 1 into 10 to the power 13. Now again, what is the difference? In one case, vibrational frequency is given in terms of CGS unit, centimeter inverse 1. In one case, it is given in the SI unit, hertz, number of vibration per second. It is hertz. So again, you need some intelligence here. What intelligence here? Because if it is hertz, so you can simply use this formula. But if it is centimeter inverse 1, so you have to do certain modification. That means you know that nu is equal to c by lambda, and this is equal to 1 by lambda is omega or omega bar. So the formula will be exponential minus hc, velocity of light is important, and then omega, values of frequency, and divided by kBt. So you must know the values of light, 3 into 10 to the power 8 meter per second. So in most of the books, what they solve it, that because this is common, Planck constant is common, Boltzmann constant is common, and T is suppose different. So what we do, if we solve it H and Kb, so we will get a common value, Hc omega, it is 1.48, that means 1.43 omega divided by T. You have to remember these things. That means 1.438 omega values, suppose given is 2360, so 2360 divided by, if it is temperature, as I have told in first part, it is temperature dependence. If the temperature is very low, so generally the values of partition function is around 1, because there is not populated, and if you increase the temperature, sometimes 2000 or 3000, there is a chance of the probability. So I will not solve all those problems. All those problems are given in different books. I am just giving you the hints that how you solve these things, nitrogen or hydrogen or iodine, everywhere you see result is 1, 1.08, 1.25. But one thing is important, that sometimes in objective type of the question where no calculation is required, sometimes they ask that the values of vibrational partition function is 2000 K and temperature is 300. Calculate the partition function, vibration. So you have to just solve it. That means, because the formula is, that I have already written theta vibrational divided by T. So you have to just theta is suppose 2000 divided by 200. So you can calculate it. 2000 divided by 200, like 20. So exponential minus 20, whatever the value you are getting, 1 minus, so it will get this final value. So thank you very much. I have already, let me summarize the thing, because it is a slight little bit big chapter and there are so many concepts here. So my summary is that don't get confused. Today I have derived the 3 formula particularly. One is for diatomic molecules using 0-point energy. Second, diatomic molecules for without considering the 0-point energy. And third, as you know, that if it is polyatomic molecules, so then of course you just have a red color, I can use these things. If it is polyatomic molecules, so not summation, the product I is equal to 1 to infinite, and S may be 3n minus 5 or 3n minus 6. Rest is the same thing, exponential 1 divided by 1 minus exponential minus h nu divided by kt. Only thing is that you have to individually consider all these things. Suppose there are 3 systems, 3 vibrational frequencies. So product of these things 1 divided by 1 minus. So my suggestion is that please refer some of the very good books so that you can understand the complete vibrational partition function. Thank you very much.